the first question on the first Castle Learning assignment. I apologize. I figured I didn't randomize the question order or anything. But again, you can just follow along here and then always go back later and fill it in. It's kind of up to whatever's easier for you. But it's 7:05, so let's get started. I actually did want to go over the first one here because the first one involves math and using an equation. So I figured it would be a good idea to hit the first one. And whenever you see the word heat, the first thing you want to think about is Q. So heat is abbreviated with the letter Q. If you're not sure or you can't remember, if you go to your reference tables all the way to the back where the equations are, everything's labeled right here. Q is heat. So there's a good bet we're going to be using one of these equations. We just kind of have to read the rest of the problem and figure out what equation we'll end up using. So back to the question here. As soon as you see the word melt, your brain should immediately think HF. HF is an abbreviation for the heat of fusion, where fusion is going to be used for any problem involving melting. And I think this term will come up again later in the Castle Learning. So as soon as you see the word melt, think HF. The equation from that, once again, I'm going to get from the reference table, is Q equals MHF. M stands for mass. Mass here is 347. So this is going to be 347 times the value for HF, which again is something you don't need to memorize. So if you go back to the reference table, we know we're using this equation right here, the Q equals MHF. If you go all the way back to the front, all these physical constants for water, table B, is everything involving those heat equations. We got HF here, which is for your melting. We got HV here, which is for boiling. And then specific heat capacity is C, which is what you'll use if you have a Q equals MC delta T problem, or MCAT, which is what I say all the time. So that's the value for HF. Go back, plug it into the equation, 334. You multiply those two together, and you will hopefully get 116,000 joules. Some of you that did this already, some common mistakes. Answer choice 4 is the answer you'll get if you use HV by accident. And then answer choice 1 is HF. So if you don't do any sort of mathematical manipulation using Q, and you just think, oh, 1 is HF, that's all I need to do, you might put that as well. So be careful. 2, not sure how you get that. I can't think of an error that would get me there. And that's it for question 1. Question 2, which sample of matter has a crystal structure? I'm only reviewing this question because particle diagrams seem to be hard and kind of confusing for people. So I'm going to draw a particle diagram for a solid, liquid, and gas, just so we can review the difference. So a solid, if we draw that out at a particle level, the key part of a solid is that I have a rigid structure. So when you put them in a container, they just have a definite shape and a definite volume. So they end up looking like this at a particle level. They're rigid. They just take up the exact amount of space that they have. And that's about it. A liquid is basically solid, and you don't need to necessarily draw them further apart. That's not what separates a liquid from a solid. It just loses that rigidity. So instead of being this solid chunk in your container, it just completely loses its shape. So you can imagine taking your solid on the left here and just imagine it falling apart almost. So it just kind of spreads out, but the particles themselves don't necessarily get further apart. And that's a common misconception. So especially when we're talking about entropy, a lot of people will say, oh, a liquid has more entropy than a solid because they're further apart. Not necessarily true. They're not as ordered as a solid is, but they're still very close together. And then obviously a gas is going to spread out and fill the entire container. That should be the easiest one to draw. For the most part, I'm most concerned with liquid. Liquid is usually where students tend to go wrong. So in terms of a crystal structure, you have to imagine a crystal is a pretty rigid shape. And in general, you don't really describe liquids and gases as looking like crystals. So the right answer should have hopefully been NaCl, solid. Some other important ones I wanted to go over. I'm not necessarily going to go over the answer to 4, but I'm going to review all the parts of 4 because that tends to come up year after year, and you'll probably see a heating or cooling curve on Wednesday. So when you see a heating curve, you got to look at your axes here, and you see that you start at a low temperature. And since you start at a low temperature, it should be fairly obvious to you that you start as a solid. So AB is a solid, CD is a liquid, and EF is a gas. Now at all those flat lines like BC and DE that have no slope, they are where your phase changes are occurring. So we have a phase change at BC. So this is a mixture of solid and liquid. That's your melting phase. And then we also have a phase change at DE. And this is a mixture of liquid and gas, which is going to be your boiling or vaporization. So some key words that pop up in questions are stuff like, in what stage is the substance only a liquid? And you don't want to say BC for that because it's a solid and a liquid. Imagine you have ice melting. You're going to have part of it being liquid, part of it being solid. You wouldn't say it's 100% liquid yet. So if you have those questions that are like, what phase or what line shows 100% solid, liquid, or gas, you're picking a diagonal line. So don't include the flat lines in a question like that. In terms of kinetic energy, your average kinetic energy, I'll abbreviate this, average KE is the same as temperature. They go hand in hand. So when you are asked questions about kinetic energy, since kinetic energy is the energy of motion, temperature is involved in the motion of particles because the higher the temperature, the faster they're going to start moving. So your average kinetic energy changes are going to be lines AB, CD, and EF. Potential energy changes are going to be your flat lines, which are BC and DE. And we call those potential energy changes because it has the potential to turn into motion. It's storing that energy to be used for another part later in some way. And in terms of a heating curve, it's going to be used to start moving again, turn into kinetic energy. So we kind of did this in class when we froze that stuff in a test tube at room temperature. You should have noticed at some point the temperature, if you remember doing the graph that you probably found annoying, just flatlined for like 10 minutes. And you kept wondering, when is it going to go down again? And we just kind of said, don't worry about it, because it would take almost 20 to 30 minutes. But during that flat line, I mean, the thing was still cooling down, but it was going through that phase change. And when you hit that phase change, there's no kinetic energy change, which means there's no temperature change. So I just wanted to go over a heating curve again. Let's see. 7. I wanted to do 7. And I think we've been doing fairly well with these this year, but when you see the word mixture, you don't want to automatically assume it's a liquid. A lot of times, students think liquids are the same as mixtures because they don't remember what aqueous means. Aqueous means you've dissolved something in water. So in the case of answer choice 4, I've taken this substance, KBr, potassium bromide, which is a type of salt, and I've dissolved it in water. And to symbolize that, since it's not a chemical reaction, you symbolize it with the letters AQ, which stand for aqueous. So AQ stands for aqueous. And when you see that symbol, your brain should go to mixture. And we're going to see that symbol a lot more towards the end of third quarter when we do solutions. But right now, all you have to really know what it means is aqueous. Question 6. So when you see questions involving ratios of elements, and you see this word varies, what that means is that these two elements are not in a fixed proportion with each other. You can throw in chromium to iron to carbon you can throw in 10 irons, 2 chromiums, 3 carbons, or 6 chromiums, 8 irons, and 9 carbons. When you see that word varies, your mind should go to mixture. Because if you're mixing things together, they're not chemically combining. When things chemically combined, you get a compound. And a compound equals fixed proportions. Because if you have H2O, for example, we call that a compound. If you change the amount of H's and O's, you're not H2O anymore, which means you're not water anymore. If you see the word varies, like I can dissolve salt in water. I can put 10 grams of salt. I can put 30 grams of salt. I can put 100 grams of salt. It doesn't matter. They're not chemically combining. So the proportion of them to each other varies. Therefore, it makes it a mixture. I'm getting like questions as I go on Remind. So if you want me to go over anything, just message me. Hopefully I'll get it in time. But yeah, thank you. I might save 8 for later. 8's an easy question. You just have to look at that particle diagram and determine, okay, that's a solid. You might not know if 1, 2, or 4 are solids at STP, but it's an easier question than it looks. A tip for question 9, anytime your temperature units don't match, like here, convert them so they're both the same. Because you might think 305 Kelvin to 0 Celsius is a huge change, but they're 2 different units, so you don't know if that's actually a 305 degree drop or really what ends up being like a 30 to 40 degree drop. So always make sure your units match each other when you're doing a problem. As you might guess, I'm going to go over 10 because they're sig figs, and at the end of the day, no one likes sig figs. So sig figs are important. The problem is we can't express how well or how important they are on a test because they're really something that you're supposed to use during an experiment or a lab. And a test can't really do that because it's just words on paper. So instead of conceptually understanding what the heck a sig fig is, you just try to memorize these rules. And of course, this is a good problem to me as a teacher because it tries to get you to know the rules with zeros, which for all the rules that exist with sig figs, you hate the most. So the first thing I usually do with a sig fig question, before I even figure out what it's asking, as soon as I see sig figs, I'm going to look at my numbers and try to figure out how many sig figs they have. 80.01 has a decimal in it. But that doesn't matter because those zeros are sandwiched. So if you have zeros that are in the middle of 2 non-zero numbers, they always count. Decimal or not, they're going to count. If this was 8001, 80.1, 8.001, doesn't matter. Those zeros are sandwiched. So every number counts in this number. 2.70. Here's the tricky one. Does that have 2 sig figs or 3 sig figs? So non-zeros always count. That should be, hopefully, pretty well known by now. Whenever you see a decimal, I don't care where that decimal is in the number, beginning, middle, end, doesn't matter. As soon as you see a decimal, find the very first non-zero that appears, the first one, and you count everything after that non-zero, including that non-zero. So these all count. Because I got that 2, I see a decimal, I'm going to count everything after that 2. This one has 3 sig figs. Now, what the heck was the question? Because we haven't even gotten to the question yet. So it's asking you to calculate the volume. If you were to do that, how many sig figs should your answer have? So I see mass, I see density, I see volume. This is a density equation manipulation. So I got D equals M over V. It's a multiplication and division scenario. And when you have a multiplication and division scenario, it's all about which of my numbers has the lowest amount of sig figs. The lowest one is 3. The answer is 3. I know sig figs are a pain. Just keep in mind, I wouldn't stress out about sig figs. It's always usually just one question year to year on the Regents. I probably said in class, last June didn't even have a sig fig question. So if you're getting stressed out about one question out of 85, unless you're aiming for 100, which is possible, try not to let sig figs get the best of you. There's other topics that are a lot more important in terms of chemistry. I might go back to 12, but I really wanted to do 14. Because again, particle diagrams are pretty tough. And it's hard to really figure out what you're looking at. So before we even look at this question and try to figure out what it's asking, let's go over the different types of particle diagrams you may or may not see. At the very least, they're going to ask you about elements. And the key with an element is think about the periodic table. It's the periodic table of elements. The only thing that's on there, if I said pick an element from the periodic table, it's that one element, oxygen. It's not bonded to anything else. If it's bonded to itself, it's still an element because there's not something different bonded to it. So there's two ways you're going to see elements. They're either going to be by themselves, so you'll see either a white circle or a colored in circle. Those are both elements because they have nothing else attached to it that's not itself. You also might see something known as a diatomic element. And before you freak out and say, what does that word mean? What does the word di mean? What does the word atomic mean? 2 atoms. So di equals 2. If it's saying a diatomic element, it still needs to be just that element. You can't attach anything different to it. So sometimes elements are going to be drawn like this. Those are all considered elements. So just keep that in mind. A compound is even easier to recognize. If there's 2 different colored things attached to each other, we assume, using this key, that those are 2 different elements. And that's the definition of a compound. 2 or more different things attached to each other. So a compound can look like this. A compound can look like this, etc., etc. As soon as you see 2 different things and they're together, 3 different things and they're together, 4 different things, doesn't matter, you have yourself a compound. So the particle diagram question is asking for a mixture of a mixture of diatomic elements. So if you see a compound, cross it out. I look at my answers, I see B. Those are 2 different things. That's a compound. That can't be a mixture of diatomic elements because one of them is a compound, which is going to be the same thing with D. Some people get confused when they look at D. They wonder if this one and this one are 2 different compounds. No, they're just oriented in different directions. Remember, these molecules are moving, like my pen can move in circles. These molecules can do the same thing. So they're not 2 different compounds. They're the same compound. Let's move on from that. So the only answer choices left are A and C. And if I just want to check myself, I see an element here and an element there because they're the same. Even though there's 2 of them, they're the same. So they're an element. And I see one here and here. So the correct answer was A and C, which is 2. Particle diagrams can be tricky. There's so many ways they could ask about it. They could ask about elements, compounds, mixture of elements, mixture of compounds, mixtures of elements and compounds. They could ask you for a particle diagram and ask for a mixture of elements and compounds as a solid. So there's just a lot of things to keep in mind. So take your time, make sure you fully understand the question, get it right, move on. We kind of went over both of those already, heating and cooling curves with particle diagrams. Let's see. These. Let's do 17, because that hits on a couple of things. Because we can talk about physical and chemical changes, and then how it applies to particle diagrams. So at the end of the day, a physical change is when you have a substance and it's just changing phase. So think of physical change as a phase change. That's usually what happens 99% of the time. If you don't have a phase change, you could have a mixture. So like food coloring in water, that doesn't have a phase change, but you can still separate the two physically. The food coloring doesn't chemically alter the water itself. You can evaporate one of them away because they have different boiling points. So physical change, think of one of two things, a phase change or a mixture. Doesn't matter which. They're both physical changes because they're reversible. I could melt ice and then I could freeze it again. I can mix salt and water and then I can evaporate the water and separate them again. Doesn't matter. A physical change is a change that is reversible and does not alter the substance. So if we look at the particle diagram here, I see 4 compounds that each look like this. So my answer choice better have 4 things that look like this. And if they don't, then that is not a physical change, that is a chemical change. And if I look at 1, 2, 3, and 4, 2 completely separated, both of them. That's a chemical change. I've taken my compounds and turned them into individual elements. 3 is I've taken my compounds, separated them, and then recombined them differently. So this is definitely a chemical change. And 4 is even crazier than 3 because I've separated them and then reattached them in a completely different way. 1, that looks like a solid to me. This looked like a gas at the beginning, so I took my gas substance and turned it into a solid. And that was 17. 18 I'm not going to go over, but I do want to focus on this word substance, pure substance. So when you see the word pure substance, that means you either have an element or a compound, not a mixture. They kind of use those words interchangeably, so just wanted to point that out. Question 20, when you get there, again, just focus on the word melting. You might get lost in the wording here. I see the word melt, I'm going to think of a certain something involving Q, where one of those equations means melting. So don't worry about that. Twenty-two. Fills the volume of any container at which it's placed. Takes the shape of the container, this is true of a liquid, but fills the volume of any container. Doesn't matter what. Liquids have a fixed volume. If I have 20 milliliters of water, I can't fill a 100-liter container. Gases will always fill the container. Sometimes we'll throw in that word uniformly. Don't freak out about the word. At the end of the day, the answer to this is 3. The 1 that is a gas. All right, let's see. I think I got a question from someone. Maybe. Nope. Okay. Moving on. Okay, so what's another good one? 25, again, I'm not going to go over, but if you see this Kelvin Celsius conversion, especially for the midterm, don't memorize that. That's on the reference table. Don't be lazy when it comes to the reference table. I am not kidding when I say I think for the most part you can easily pass, which I know shouldn't be your goal, but you should be able to pass if you can effectively use the reference table and all the information it has to offer. So temperature conversions are on the reference table. That is a plus sign, not a multiplication, not a division. So if you're given Kelvin and you need Celsius, just subtract 273 from both sides. If you're given Celsius and you need Kelvin, the equation should be very obvious for what you need to do. I'm approaching the end of this first Castle learning. I'm going to take about a few minutes here to review naming and formula writing, because you know that's a pain in the butt. So if you're good with naming and formula writing, start looking through all these other questions and seeing if I missed something that you'd prefer me to go over. If not, just hang tight. We'll get to the second one, probably get about halfway through it, and then call it a night. Because I really don't want this to go longer than an hour, because I'm sure I'm going to start losing some of your attention. You have a math midterm tomorrow, a lot of you. You should be focusing a little bit on that too, because those are important. And yeah. So the first thing I need to point out, when you see that stupid word IUPAC, pretend like it's not there. IUPAC is the name of the organization that comes up with these rules. It has no importance to you other than making you know these rules. So if anything, you probably just dislike them. So if you see the word IUPAC, just completely ignore it. And as soon as you see naming something, you have to either check their charges. So always check your charges. And this is going to be super, super important in third quarter, because when we're doing chemical reactions and these substances are exchanging atoms with each other, you're going to have to either name them or write their formula or something where you have to check their charges in some way. 2, check table E. Those are the two most important pieces of information I can give you when it comes to naming. Because those Greek prefixes, you're not really going to see all too often. It's mainly these ionic compounds. It's mainly something that's a metal and a non-metal, where you have to check their charges, crisscross them, etc. 26, I think, is pretty easy, because you don't really have a choice. Oxygen, any atom from the periodic table. So your metal in your formula, which is always going to be the one on the left, you just name normally. Zinc, iron, calcium, whatever. Your non-metal, which is oxygen here, you have to change to "ide." So you change the ending to "ide." So never say zinc oxygen. It's just going to look silly. I think you should be hopefully familiar with what these compounds' names are, since we talk about them so much in class, that you've never heard something called zinc oxygen. So I see oxygen, that changes to oxide. I think 26 was on the easy side. This is on table E, table E, table E. So the other three answers were all table E compounds. Okay, iron 3 sulfide. A big testing strategy I tell my students, especially when I'm tutoring SAT and ACT, is to predict your answer before you look at them, so you don't let the answers influence your decision. Because if you see iron 3 sulfide and the first thing you do is look at these answers, you're going to get a little stressed out, because you might see answer choice 4 and go, is sulfide SO3? Try not to look at the answers. I know it's hard, but try not to. When I see sulfide, I don't see it ending in TE, and we know if it ends in TE, you're going to table E. And since that doesn't end in TE, I'm not going to go to table E. So sulfide must be sulfur. Iron is Fe. let's say it's test A. You get to this question, it's a short answer question. You don't remember the chemical abbreviation for iron. Or you're like a lot of my students on the periodic table quiz we just took, and you thought potassium was P. If you can't remember the chemical symbol of an element, go to the reference table, go to table S, and this table S is organized by atomic number. And what does the second row say? Symbol. So if you ever forget a symbol, you're like, wait a minute, what's potassium again? What's iron? I know it's not I. Go down table S, iron's right there, and it's Fe. Again, is it tedious? Yes, but chemistry is not easy. This shouldn't be like a cakewalk when you first enter this class. Take the time to get it right. The more you do this stuff, the more better, that was a terrible way of wording it, the better you'll get at it. Because no one's really proficient at this the first time they do it. It takes some practice. So don't worry about if you haven't memorized the elements yet. Look it up. All right, back to the question. Iron 3. The 3 does not mean this, which isn't an answer choice, thankfully, but you know that's probably going to be one on the midterm where they put an answer choice like that. The 3 does not mean that you have 3 irons. So please don't do that. The 3 means you have a charge on your iron that is 3. Because if you go to your reference table and you find iron on the periodic table, iron has 2 choices for its charge. So when you name any compound with iron in it, you have to specify which iron it is. Is it +2 iron or +3 iron? And that is true for any elements in here. Any of the elements in here, when you name them, any of the ones I've highlighted, when you name them, you need to put a Roman numeral with it and tell me the charge, or you're wrong. You don't need to do that with the nonmetals because they're always going to be negative when they're with a metal. And other than nitrogen, most of them only have 1 negative charge. Nitrogen, always pick -3. I don't think you'll ever see it not be -3. I don't know why they give you all the other ones. You don't need to do that with groups 1 and 2 because 1 and 2 each only have 1 charge. So group 2 is all +2. Group 1 is all +1. You don't need to say lithium 1 oxide because lithium is always +1. So don't worry about it. Which is the same reason why in the problem beforehand, zinc 2 oxide wasn't a choice because zinc is always +2. So look in that highlighted region, see which ones have more than 1 charge, and if the answer is yes they do, you got to use the parentheses. So back to the problem. Iron was +3. Sulfur, if I look that up, is -2. Now you crisscross, which is a trick. You're not literally taking a +3 here and a -2 here and bringing them down and putting iron -2, sulfur +3. You need to cancel out these charges. Mathematically, you're finding the least common factor, greatest common factor, whatever. I don't know. But a trick to do that is to just take the 2 and put it here, take the 3 and put it there, and you get Fe2S3, boom. Take your time with these. Naming is a big pain. It's a huge pain. It was a pain for me. I remember in college, when you take organic chemistry for any of those pre-med students or future pre-med students, or you're thinking about going pre-med or pre-health, you spend so much time on nomenclature. It gets annoying. I apologize. But take your time, get it right, move on. I think we tend to struggle a lot with this. When you have to sit there and try to predict what X is. And I would highly recommend, and not a lot of students do this, look at the elements they give you, plug them in, and see if that makes sense. Is that annoying? Yes. I'll go over the quick way first, but if you want a guaranteed way, multiple choice, plug the answer choices into your formula and see if it works. And then if it does, you're done. That's the right answer. Don't be afraid to substitute the answer choices in to the question. You'll get it right. How would I do it if it's a short answer, for example? If you don't have if it's not multiple choice and you don't have the answers right there, I see XF2, which means I have 2 fluorines. So I have some unknown element X that's trying to balance out 2 fluorines that are each charged -1. So that's a total of -2. Well, based on my formula, I have 1x. Don't change your formula to try to make it correct and easier for you to solve. I see 1x trying to cancel out a -2 charge. My x better be +2. So I got to go back, look at my answer choices, and pick an element that's charged +2, which in this case is magnesium. Don't pick argon. Argon's a noble gas and it doesn't react with anything. If you don't remember to do what I just did, and it's multiple choice, go to the periodic table, look up these 3 elements on the periodic table, and look at their charges. We got +3, +1, and +2 for each of these. I'll make it a different color. +3, +1, and +2. These are the 3 elements that we're discussing in the question, because we already ruled out argon, because argon doesn't react. So I'm going to go back, write magnesium's +2, sodium's +1, aluminum's +3, and I'm trying to balance this equation here where my X I have 1 of, and my fluorines there's 2 of. Well, if there's 2 fluorines, and you know 1 fluorine's -1, again, I'm trying to cancel out that -2. Magnesium is +2. Boom, cancel, done, circle it, get it right, smile, move on. So 29, I'm going to leave to you. Take your time. 30, all I'm going to say for 30 is that ends in TE. I'm going to table E. And when you go to table E, put it in parentheses. I have phosphate, which is PO4, and that as a whole has a -3 charge, all by itself. So do not start doing 4 times 3. Don't do that. No. Bad. I'm going to put sad face in the circle in the O. It's bad. So don't do that. You still crisscross normally. Keep the parentheses on your phosphate. Keep your parentheses on your table E stuff. And just, again, take your time. It's no rush. The midterm's going to go a lot faster than you think. Chemistry tests, especially the Regents, aside from maybe like 5 to 8 questions, they're really quick answers. You don't really do as much writing as you think you're going to do, and you don't think you're going to do as much math as you think you're going to do. The midterm might be more heavily weighted with the math than the Regents, because the midterm is carrying over from the first 2 quarters, which is where we kind of front load most of the math. But the Regents, year to year to year, there's like 10 questions where I see students, I would say, needing to use an equation of some kind. So it goes quicker than you think, so take your time. Before I move on, any questions, feel free to send me on Remind right now, and I will answer them as best as I can. How many people we got? 16? I'll take it. It's better than nothing. I'll take that over 0 any day. Again, tell your buddies if they couldn't make this, that they can always just, I'm going to post this on my teacher site so they can watch it later if they choose to. So if you have any questions on Remind, I'm going to take like a quick 1-minute break and just sit here and wait for questions. And if there are none, I'm going to move to the second one where I'm going to do a few, but not all, so we can save some for tomorrow. And maybe we'll make this like a bit longer tomorrow. Because again, you have math midterms tomorrow. Most of you. So you need to focus on that. All right, I'm going to take the lack of texts as Mr. G, we're good. Let's move on. So I'm going to move on. And actually, before I even do these graphs, I'm going to cover the gosh darn atomic models because we can't remember that very well. And so let's cover that. If you see a question like 2, when it's multiple choice, kind of ask yourself, or say to yourself even, the first discovery is probably ions, polar and nonpolar. I'm not doing polar and nonpolar today. I'm doing that tomorrow because that's involved with bonding, and that's big. So I'm definitely not doing it tonight, but I'm definitely going to do it tomorrow. So don't worry, we'll get there. But let's take our time. If you see anything with atomic history, say to yourself, the first discovery is probably the simplest discovery. And the simplest discovery should be D. I didn't want to cross that out. I wanted to highlight that. The simplest discovery should be D. Atoms are hard spheres. This guy's just saying atoms are like tennis balls. No. That's wrong. Can you imagine if that was just in your body? I can't even imagine how he even jumped to that conclusion because you would probably feel that inside of you since everyone is made of atoms. So there's no way that D is not the first one. So these two are out. The next 3 are arguably the most important because they come up year after year after year after year. So B, that was Thomson. He discovered the electrons. He used a cathode ray tube in his experiment. You might see the term cathode ray. You might see the term electron. You might see it worded like B here where it just says negatively charged particles. So that was Thomson. He did that plum pudding model, which doesn't, I think that's an analogy that doesn't make sense anymore. Think of it like a chocolate chip cookie. He thought the electrons were like chocolate chips that were just running around this cookie and that's what he thought the atom looked like. C, that's very popular. Rutherford. So C was good old Rutherford, and his experiment involved gold foil. And he fired these alpha particles at it. And he noticed that the alpha particles mostly just passed through the atom. And then every once in a while, they would shoot back in a different direction. So he said the atom was mostly empty space with a small dense nucleus, which they have here in C. That's a pretty popular one that pops up all the time. And then A, electrons have wave-like properties, is what we associated with Schrodinger, but Schrodinger's name doesn't pop up really. What does pop up is the word orbital. And when you see the word orbital, you think probable location of electrons. Not orbits, not a planet. This is an orbit. Orbitals describe how electrons are like waves, which means there's a chance that it's somewhere in here, but we can't usually say for certain what its momentum and location is. So you usually see this word orbital pop up often. So D is clearly the simplest one, which is probably first. A should be the most complex, making 4 the right answer here. Let's see. Gases. Ideal gas. I'm not going to go over every question involving ideal gas, but you need to know the properties of ideal gas. And these are kind of frustrating because really after this unit, we kind of talk about it again later, but it doesn't pop up too much. So this is one of the easiest things to forget. First thing, high temp, low pressure. Ideal gases are most ideal at high temperatures and low pressures. So if you take real gases, like gases that exist in our atmosphere, and put them in increasingly high temperatures and in decreasingly low temperatures, or increasingly low? I don't know how to say that. You start to see these patterns where they move in random, that was bad. Let's clean that up. Random, straight motions, not predictable, circular. So don't confuse random and straight. They're two different things. You cannot predict where they're going, but wherever they're going, they're moving in a straight line. Some people think that random and straight oppose each other. They have nothing to do with each other. They're two different things. Have no attractive forces between them. That's correct. They do transfer energy when they collide with each other. They are separated by distances that are very large. I didn't know how else to reword that to fit the opposite of that answer. But they are very far apart. And then the only other thing that's not here is they have small volumes, which you would associate with the word negligible. That's the one that popped up all the time, was the word negligible. So they have very small volumes. So I just wanted to review ideal gases because we know that's going to pop up for sure. Let's see. 7. And then we'll do 9 and a few. Don't make 7 harder than it is. Just think about the volume of anything. If you have 3 liters of anything, that's going to be the same as 3 liters of anything. It's just volume. So if I have 3 liters of hydrogen, the thing that's going to be the same as that is 3 liters of any other gas, because gases fill a container. Gases, there's not the rule of gases fill a container unless it's something else. If I have a 3-liter container and I fill it with hydrogen, and I have a 3-liter container and I fill it with what's methane here, that they have the same amount of stuff in it. It's just volume equals volume. I always give that analogy, and I know they're liquids, but it's the only good analogy I can think of 2-liter bottles of soda. You have a 2-liter bottle of Pepsi, a 2-liter bottle of Mountain Dew, 2-liter bottle of Coke. Yeah, they're different sodas. That doesn't matter that they're different sodas. They have the same volume, so they have the same amount of stuff in it. So, don't make 7 harder than it is. Pops up a lot, year to year to year. I think this one is easier than others, but what really gets confusing if answer choice 1 didn't have NH3 and also said H2, and kids just want to go, oh, it says H2, it's got to be number 1 because they're both H2. No. Pick the same volume. Atoms versus ions. So someone asked to go over ions. I'm going to go over ions because we're still at best with ions. Atom. You see the word atom. That means your protons equal your electrons. So don't look at the charge on the periodic table. So you look at potassium, it's going to have 19 here, 39.09, I think, there, and then a +1 here. And you get to the word atom, and you are going to ignore this. Ignore it, because then it's not an atom. K plus 1 is an ion. We got to keep these two terms separated because we're not at the moment. So, K plus 1 is an ion. K is an atom. And if you're an atom, your protons and electrons are the same. Because atom means you are not charged. So your positive charges and your negative charges have to be the same. How do I know how many protons K has? This is K's atomic number. That is your protons. 19. Take your time and really make sure you understand the difference between atoms, ions, atomic number, atomic mass, protons, neutrons, and electrons. If you look at the reference table, be careful, but if you look at the reference table and you go to table O, they have protons and neutrons here, where you can see that the neutron has a mass but no charge. I encourage you to use this. Sorry, my stylus is too fat to write clearly. Anyway, use this as a last resort because this doesn't really pertain to any unit we've covered yet, and it's not like they label what these numbers mean. So if you forget, you kind of dig yourself a hole. But you can check there as a last resort, and that's all I'm going to say. If you're wondering if electrons are on here, technically the answer is yes. I'm not going to point it out because there's two things that say E, and you're going to get confused. So I'm not going to do it. Hi, Rob. Rob wanted a shout out. So how you doing, Rob? I hope you're having a great night. I hope your midterms went okay today. I hope your midterm goes great tomorrow. Also, Cole, if you're watching, the model kits lab that was due like a month ago, probably even longer than that, that's the one where you had to draw all the structures on it. It says model kits lab on it. So I can't show you what it looks like right now, but you should have turned that in before January. So good luck finding it. And if you're not watching, someone that knows him, can you just tell him I said that? That'd be appreciated because I feel like ignoring him right now because he should have turned that in a while ago. Anyway. Last thing I'm going to cover tonight, I'm going to do 17. 17 and 23 because those are good ones. And then I'm done. And you're done. And you need to go study for geometry or algebra 2. So, 17. Aluminum plus 3. So, first, they don't give you aluminum's atomic number, so you really can't figure anything out about electrons if you don't know how many protons it has. So you're going to go find aluminum on the reference table, go to the periodic table, find good old aluminum, and boom! 13. So, aluminum's atomic number is 13. You're going to see this plus 3. And some of you are going to go, oh, it has 16 electrons because 13 plus 3 is 16. No. Incorrect. Because protons are positive, electrons are negative. Okay? Protons will never change. If you change protons, you change your element. You're not aluminum anymore. So the first thing you got to say to yourself, hi, Lucas. You want a shout out as well? This is your shout out. I saw you today. Thanks for stopping by. I'll probably see you again maybe tomorrow or later this week. I don't know. But this is your shout out. I hope you enjoyed it. So if this was an atom, we would say the protons equal the electrons. This is not an atom. Not only does it say it's an ion, but it gives you the charge. You got two options here. So we have 13 protons, 13 positives, which typically means you would have 13 negatives. But it says as a whole, you're charged +3. So you've lost 3 of something to make it positive. And the only way you can become positive and stay as aluminum means you didn't lose protons, you must have lost electrons. Because if I have protons and 10 electrons, well, I got 13 positives and 10 negatives, and 13 minus 10 is good old +3. So you have 10 electrons. If someone comes up with a really good analogy to remember this, that would be awesome. Because I haven't figured it out yet. +3 does not mean you've gained anything. You've lost. When you see +3, you lost electrons. Last one. Which one did I say? I'll see it. I probably passed it. Sure did. 23. I'm going to actually go over 23 differently than what the problem's asking, because I want to make sure we keep clear of all of this. I'm going to ignore this part of the question, and we're going to tackle it step by step by step. Question 1. Atomic number. If it asks you for atomic number, that is the same as the protons, 8. Okay, atomic number should be easy. I haven't seen too many issues there. If it asks for mass number, mass number is protons and neutrons. And 9 plus 8 is 17. You shouldn't need a calculator. So mass number is protons and neutrons. And however that's organized, if you see mass, protons and neutrons. Last but not least, charge is something involving protons and electrons. And in this scenario, we have the exact opposite of what we had here. Here, we had less electrons than protons, which gave us a positive charge. Here, we have more electrons than protons. So if I have 8 positives and 10 negatives, I have 2 more negatives than I do positives. 2 more negatives, 2 more negatives. And that's it. Hi, Mrs. G.
Hi, Mr. G.
Welcome home.
Thanks.
You know, I did get a request for some kids. They wanted to see Harper. I don't know if these students are online right now
Harper.
to see Harper.
Come here.
But Harper can come make an appearance.
Harper, come here.
Harper!
She's not worried about it. Hey, what about her?
Yeah, she's sleeping.
You want to come make an appearance?
Any questions before I sign out?
You got a celebrity appearance.
Harp, come here.
She doesn't know.
I know I'm on a little...
Harper.
Harper, I'm right here. What are you doing? Come here.
Oh, she's so tired.
Come here. Hey, you gotta go say hi to Mom. Just gotta say hi to Mom. You're welcome. You know who you are. Harper, come here.
Go. Go get
Come
it.
say hi. Come say hi. Come here. Come on. Up, 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 up. Oh, come on. You can do it. Up. Oh, there we go. Look at that camera. Oh, no, you're not on camera. Oh, there you go. Oh, there she is.
I don't want to be on camera.
Yeah, hey, no. And then say hi. Hi. She's like that. All right. Everybody, go study for your math midterms, okay? We'll do this again tomorrow. We'll do it longer tomorrow because the only midterm you should have Wednesday is my class unless you have Spanish. What else is Wednesday? I don't know.
I think that's it.
But go relax for a little bit. Study up for math. I'll see you later.